Great. So let me welcome you to the Stewardship Network's monthly webcast. I am Lisa Brush, and I'm really pleased to be here today with Steve Apfelbaum to talk about soil carbon management and grassland restoration. And let's see, as my computer is just getting here, let me offer you the chance to introduce yourself. Let us know where you're tuning in from. Great to have you with us, and drop where you're tuning in from into the chat, and we will have a chance to be together for the next hour. Let me tell you just a little bit about the Stewardship Network if you haven't, if you don't know us, and my computer's being a little laggy here, but our mission is to connect, equip, and mobilize people and organizations to care for land and water in their communities. And so we are capacity builders that help keep you all out in the community doing your stewardship work, connecting you, providing you with the resources to do that work and stay engaged and learn from each other to accelerate and amplify the work that you do. We are a national and international award-winning nonprofit that works all across the country now. You know, if you tuned in 10 years ago, we would have said the Great Lakes, but now we work all across the country. And we are looking forward to kind of constantly advance the work that you do. As you all know, that partnerships and collaboration is the name of the game at the Stewardship Network. We work with all volunteer NGOs to international NGOs, municipal, state, federal, tribal governments, consultants and contractors, nonprofits of all kinds, and private property owners, individual, everybody that cares for land and water is part of the network. Our member communities are locally, geographically based networks made up of all of the people who care for land and water that do on-the-ground conservation action and kind of learning and engagement to get to know each other in the community, to accelerate the work that you do. And then we help connect, we provide the backbone support for those communities, and then we help connect those communities so that you all can learn from each other and share the great ideas that you have to amplify your work. So if you are in one of our member communities, great, I love the chance to know you. And then if you're not, let us know if you'd like to start one. I also want to support financial contributors to the Stewardship Network. As I said, we're a 501c3 nonprofit, and so your support enables us to continue to do things like broadcast these free online monthly webcasts each and every month, as we have been doing for 15 years. I think this might be 15 years. And back when we didn't have iPhones, back when this kind of technology wasn't the kind of thing that we did all the time. So thank you for your financial contributions. Really appreciate that. We bring everybody together in person each year. And last year we did that virtually, and we are going to do it again virtually in 2022. It just feels like it's a little bit too unknown to know what it's going to be like to bring 450 people inside for 3 days. We had a really successful virtual experience last year at the beginning of January. People said it was one of the best online experiences that they've had. We were able to really recreate a lot of the experiences of being in person, just not in person. We had to be like this virtually. So we're going to do that again. We have our call for presentations open. We'd love to hear the work, the research that you are doing. And the deadline is Sunday, August 8th for the call for submissions for abstracts. So the other thing that we do is we do a spring challenge. And the spring challenge, as many of you know, is one of the ways that we really show the collective work that we all do. So sometimes this work can feel overwhelming, the problems can seem so big, and you don't have the answers. You may feel alone in your work and trying to convince your decision makers about the work that you do. And so we do a spring challenge to show the collective impact of all of the work that we do. So I want to briefly announce the winners of the 2021 Spring Invasive Species Challenge. So congratulations to our lightweight winner, the Put-in-Bay High School Environmental Club and the Lake Erie Interpretive Center, I think is what that one is. So congrats to Put-in-Bay High School Environmental Club, to our middleweight division champions in New York, the Lower Hudson PRISM, the Partnership for Regional Invasive Species Management. So congrats to you all. And our heavyweight division goes back to one of our previous winners. Congratulations to Ann Arbor's Natural Area Preservation. So thank you all for the work that you do for that. Really appreciate your participation and the impact that you have. So thanks again for all of your participation, and we'll see you next year for that. And with that, I want to remind you, I'm Lisa Brush with the Stewardship Network, and I'm really pleased to be here with Steve Apfelbaum with Resource Environmental Solutions. Steve, I'm going to stumble over that. Steve's firm, Applied Ecological Services, which has been a leader in the field for decades, was recently acquired by Resource Environmental Solutions, offering even more ability to do credible stewardship and ecological restoration all over the globe. So Steve, thanks so much for being here. Really appreciate it. And again, I want to encourage you all to go ahead and share your questions as they come up and introduce yourself. Let us know where you're tuning in from. And with that, Steve, I'm going to turn it over and you'll share your screen.
Okay. And all I have to do is figure out how to show the slideshow function.
Yep. And great, Neil, to have you here from Ann Arbor, and Maggie, one of the former employees with Steve at AES. Great to have you with us. Betsy, good to see you tuning in from Southwest Pennsylvania. Emily, great to have you back. It's always nice. We have returning webcast attendees, and then we have folks who are new to it. So Peter, great to have you here from Sudbury in Canada.
So Stephen, it's right up at the top. If you see that on switch about 4 icons over.
Yeah.
That little play button.
There's a, there it is. The black toolbar was covering it up. So thanks, Rob. And let's see if it'll, everybody got the screen?
Yep, you're looking great.
That's great. So I'm ready to go, Lisa, whenever you suggest.
You are ready to go.
Okay.
I'll mute myself and I'll stay tuned for the ride.
So what I wanted to do is dance lightly across the tip of the icebergs of a very deep and very, very important subject about soil and soil carbon, and how grasslands have evolved with grazing animals, and how the interaction between grazers and grasslands and soil microbes have created this ecosystem that a lot of us work in, called grassland ecosystems. The grazing nexus with soil goes well beyond grasslands. We'll focus on grasslands today. So what a group of us, I'll go back to that slide, a group of us were invited to present what I believe was the last science presentation presented at the Barack Obama White House. And we were reporting on new research where we were studying basically how grazing of livestock could be used to emulate the way large herds of bison and caribou and wildebeest did graze and still graze in some parts of the world, and what those relationships are with the really high density, intense grazing. So Dr. Richard Teague from Texas A&M, Peter Bick from Arizona State University, and a large group of people from Shell Oil Company and 10 other research institutions participated in this presentation at the White House with the Office of Science and Technology. And we basically walked in with a research project that we were providing preliminary reports. And the premise of the research, the working hypothesis, was that carbon-rich soil is healthy and beneficial for the entire ecosystem. And that really the ultimate solution for food quality, food security, climate risk, climate mitigation on the planet, in fact, may rest with rebuilding soils on the planet. And tapping into that age-old, at least 2 billion-year-old experiment called photosynthesis that we all know so well. And so do the bacteria and fungi and every other organism on the planet. They all rely on it in one way or the other, as do soil systems. So when we draw down CO2 from the atmosphere with the photosynthetic process, and methane and nitrous oxide that is also drawn down by microbes into the soil system, we build healthy soils, we build the co-benefits that we benefit from of having healthy soils, food and water, and a range of other things. And if we're a farmer or a rancher, if we eat or benefit from the food they produce, benefit from the improvements in soil health. So first thing I thought would be useful is to give you a little bit of carbon science. In rough numbers, and these numbers, they bounce around. I think the numbers are actually a little higher now, but basically we emit anthropogenically about 9 gigatons of greenhouse gases, CO2 and others, into the atmosphere every year, and about 4 remain annually. So a little less than half remain. And the balance is, it roughly splits between what goes into the ocean as a dissolved form of carbonic acid, is what becomes the carbon dioxide, and then what becomes of the soil systems and you and I and all the other life on the terrestrial planet. So about 2.5 roughly, and 2.5 go into the ocean and terrestrial ecosystems, and about 4 remain in the atmosphere annually. Let me see if I can change the slide. Uh-oh, technology problem. There we go. If you scale proportionally where the carbon stocks are present on the planet, you see the big blue circle. You're only seeing a part of it. It's a massive blue circle. You know, the majority or a large percentage is in the oceans. But then the second largest percentage of the carbon on the planet, the living carbon, not that's fossilized in limestone, for example, the living carbon is in the soil systems on the planet. And you can also see that pastures represent a pretty substantial part of that. The plants represent a small part of that. The atmosphere actually also represents a small part compared to the entire mass balance. There's about 3.5 billion hectares of pastured land on the planet, both native grasslands and cultivated grasslands, and about 1 billion hectares of croplands on the planet. So in rough numbers, just to keep it simple between all of us, let's just say there's 5 billion hectares of land that we routinely manage as human beings in our various myriad forms of civilization around the world. You know, we manage pastures, we manage orchards, we manage annual crops, perennial crops. And what we hypothesized was, here's the distribution of those 3.5 billion hectares of grasslands and 2 billion hectares of agricultural lands on the planet. What we hypothesized was, what if we could take the average carbon level in soils on that 5 billion hectares, let's just stick with 5 billion hectares, and increase it by 1 ton per hectare per year. Well, 1 ton per hectare per year added to the average, which is about 100 tons of carbon per hectare. That's the average in according to USDA in the US and Canada. If we take and add 1 ton, that's a 1% increase annually that would be added to the 100 tons. Well, if you add 1 ton to 5 billion hectares of land, you're adding 5 gigatons of soil carbon right to the soil, and that carbon is derived from the atmosphere through the photosynthetic process. So this got everybody on our team excited. You know, we weren't being idealistic and saying, well, we're going to get every acre of all that pasture and every acre of all that cropland doing this work of building up soil carbon by 1 ton per hectare per year. I'll show you what we did with that. But we thought, wow, this is really feasible if the human hearts and minds and, you know, behavioral changes on land use and land management could change. This is absolutely doable. Changing a farm field from having, you know, 100 tons per hectare to 101 tons per hectare on average is very, very simple. So we began looking at just how real the opportunity was and did 3 primary studies. I'll report on the one in the southeastern US, where we measured 2.5% increase in carbon per year over a 6-year period. A project in the Northern Great Plains, a preliminary project where we reported 1.1 tons of carbon. And then Dr. Teague's seminal paper where he reported about 1.7, just under 2 tons of carbon per hectare per year. Under all of these projects were under the grazing practice that we're going to talk about here. So is it possible to build soils at a rate of about 1% or 1 ton per hectare per year? Absolutely. And the 0.4% carbon gain per year that the food security and climate goal that the EU and the French government came up with was leaving a real value proposition on the table. They were discounting what they could do by half. So what we did is we turned to the ranching community and we said we would like to find the best ranchers that are emulating as close as possible the way historic herds of native ungulates, native ruminants, bison and so forth grazed. And with the help of Alan Williams and Gabe Brown and many ranchers, we decided to settle the initial research focus in 2 places. One was Alberta and the other was in the southeastern US. And I'll give you I'll use information from both, but report on some of the southeastern US studies. So the first thing we began to learn through the whole process was that more than 90% of the soil function is mediated by microbes, and the microbes really do depend and have coevolutionary relationships with plants, and so do I'm including soil fungi under that category. How we manage plants is thus critical, and if we till the soil and disrupt structure and functionality of the microbe communities and the structure of the soil that they and the plants and climate have created and the grazing animals have created, then we actually measure very predictable declines in soil organic carbon. So most of the Corn Belt, what we have measured in most of the Corn Belt where we've sampled, the soils are losing about 2 to 4 tons of carbon, not carbon dioxide equivalent, but carbon per hectare per year. Even conservation tillage, like chisel plowing, is on average losing about 1.7 tons per hectare per year. No-till agriculture, depending upon how it's done, is either losing or gaining. And no-till agriculture is a catch-all term, and there's no such thing as one type of no-till agriculture. We could talk more about that later if you want. So what we set out to do is measure 4 ecosystem process related and functional measurements. We wanted to understand energy flow, water cycle, mineral cycle, and plant and animal community dynamics. And the first thing the research group did was we went around and visited some of these really avant-garde ranchers and farmers and began learning from them immediately. They are remarkable. And, the academic community is well behind where the agricultural community is advancing rapidly. And even the marketplace is well beyond what consumers are hearing. The marketplace is moving some sectors faster than others. So the picture on the right is the exact same location as the picture on the left was taken. And completely counterintuitively, no seed was added, no irrigation, no fertilizer. The only thing was added to convert from the picture on the left to the picture on the right was to increase the cattle density by 5-fold and run the cattle over the image on the left very rapidly. They broke up the soil crust that you see, and that allowed water to enter. It stimulated the seed bank, and the seed bank response is what you see in the image on the right. No restoration other than livestock management, and it's remarkable. So the image on the left was a continuous grazing where the cattle were out there and the cattle went and did whatever cattle wanted to do, and they kept going back to the choice grazing locations. The choice locations were depleted And it was a net emitter of CO2 and nitrous oxide, methane, and all the water, a large percentage of the water ran off. The image on the right, absolutely opposite performance. And I'll give you some data to demonstrate that. What Richard Teague did in Texas was really intriguing, and that informed the research team. He put GPS collars on cattle. So every green dot is a GPS registration of a cow working over, I think this was a 5,000 acre pasture in northern Texas. And what he learned, and he knew it before he did the data collection, was that the cattle, if they're continuous grazed, they're allowed out into a pasture, and they really do have preferential areas. And they go to those areas and really don't spread out their impact over the larger paddock. So he also taught us some really interesting factoids that I didn't really understand initially, but it makes so much sense. Overgrazing has little to do with the number of animals. It has to do with the amount of time plants are exposed to the animals. One cow grazing on 10 acres all season can kill thousands of plants, but 1,000 cows grazing the same acre for one day will not kill a single plant. And this is the fundamental lesson that I had to learn, because I viewed overgrazed land with disdain and didn't really understand how it happened. I just thought, it's a farmer that's making bad decisions. Well, it's true. It's not the cow, it's the how. It's how the cattle or the livestock are being managed. And that is a human decision, at least. So what Richard did is he broke the landscape into small paddocks. And you can see the dashed lines representing the paddocks. And there's a watering location for the cattle. You can see with the water points. And he got the cattle to disperse their grazing activity over each paddock and did it very quickly, a day or so in each paddock. And then they were moved to the next paddock. And then they didn't come back around to the same paddock for probably 60 to 90 days. So the recovery period was adequate and appropriate for the plants below ground and above ground to respond to the grazing stress. So what we did, just to switch to a couple of the projects, the one project we did was trying to understand grazing, soil carbon, water relationships, and greenhouse gas emissions across 4 ecoregions in Alberta, where the little red stars are. They're all very different. The further west, the leftmost stars are the foothills of the British Columbia Rockies, the Albertan Rockies. And then as you move out to the east, you're out in basically northern Great Plains, dry and also moist northern Great Plains grasslands. And what we did was many things, but I'm going to give you a snapshot. The first thing we did was in an operating pasture in each of those locations, we have an adaptive multi-paddock grazed pasture. So that's a new term. That's the term Richard came up with that is the name for the type of grazing a herd of bison do, or a herd of caribou. He's added the human decision-making by adding the word adaptive management, because it's not formulaic. You have to look at the condition of the rangeland. You use that to determine how long your animals are out there on a paddock. And then you make adaptive decisions every day, every year in each paddock to respond to the conditions on the land. So what we did is we had adaptively managed pastures right across the fence or near enough in the same soil type, same biophysical setting. And the primary divergence was that oftentimes the one brother or one family member of the same ranch decided to continuously graze, do things the way they've always done it. And the other brother or family decided to do this adaptive multi-paddock grazing. So we set out over those paddocks. In the upper left image, the little zeros or points you see on that air photograph are the random points that were sampled for hydrology and sampled for soil carbon. And the photograph right in the middle is Rye Thompson and others from AES with one of our hydraulic sampling units sampling 1 meter depth soil core samples, which were then taken to a lab and taxonomically broken down by strata and then measured for total carbon, or organic carbon, inorganic carbon, and some other chemistry. At the exact same points, we plugged that unit you see in the upper right, which is an automated dual-headed infiltrometer into the soil. And the white bucket is a reservoir of water that feeds water into a computer. And then you can see a kind of a silver circular unit. That's like a pressure cooker that's plugged into the ground. And the water pressure in that pressure cooker is what achieves the head that's used to test infiltration into the soil. The other thing we did was we used carbon-13 isotope pulsing. So that little canister you see in the middle center photo, little tiny, canister, steel canister full of carbon isotope 13 was pulsed into those plastic tents you see out in the field to the left. And then over a period of 6 months in real time, basically the soils, the soil microbes, the plant, above ground, below ground, the cattle, and then air emissions above the site, above the adaptive grazed and the conventional grazed were monitored. And using this isotope analysis, we could trace, where the carbon went into the system with photosynthesis and how it was routed all the way down through the soil microbes and into the groundwater and outgassed as CO2 and methane. And we were able to put together mass balances. And what we found out was, one thing that I don't have data to share with you yet, but I'll give you a sneak preview. We found out that the herd of cattle that worked right through the area when we were doing the work multiple times, the methane they were emitting, belching and other things cattle do, in real time, methanotrope bacteria were completely sequestering that. It looks like nearly zero net methane emissions, which is really very different from what happened on the conventional side of the fence, where that methanotrope cloud and microbe relationship was either not present or not as viable, and there was a net methane emission. And we'll be reporting on this. We want to get the science right, because this is one of the very first reports on the planet that's differentiating, that ruminants actually do have a relationship, and methane is a very, very important byproduct of their activity, and nature's figured out a way to deal with it in healthy ecosystems. So what we've learned is that energy flow, water cycle, mineral cycle, and community dynamics are completely different in this adaptive multi-paddock grazed situation. The lower image is an adaptive multi-paddock grazed pasture, and the upper right image is a conventionally continuously grazed pasture that's not been overgrazed. But what you see is a lot of standing crop, a lot of biomass that's dead, a lot of litter on the ground. There's very ineffective energy flow. The photosynthetic, the solar collection apparatus, all the leaves and foliar systems are a large percentage is completely obscured by litter and dead plant material, where the grazing is continuous conventional. The water cycle, I'll tell you in a minute, and the mineral cycle, we'll talk about in a little bit. But what we measured right across the fence, everything identical except the grazing practice, for at least the past 10 years, everything identical except the grazing practice, is about 2 tons of carbon per hectare per year increase occurring in real time with the adaptive multi-paddock grazing. And what was interesting, I won't take you through it, but not all carbon is the same. Most of the plant material breaks down into what's called particulate carbon. That's like mulch you put on your garden. And that stuff typically disappears like mulch you put on your garden within a year or less. Particulate carbon has a very short durability. It turns over rapidly, usually 2 to 3 years. Some's a little longer lived. But mineral associated carbon can last thousands to hundreds of thousands of years. And what we learned was that nature's use of this herd grazing practice actually puts significantly more of this mineral associated organic carbon into the system. So the long durable carbon, which is really fantastic. The other thing we learned is here's 2 profiles. And I won't give you a lot of information about this, but a planted pasture planted with non-native cool season grasses like tall fescue or European brome and red clover would be represented by what you see on the left. And the native warm season, cool season grass pastures is what you would see on the right. So the green line down to a meter depth is the carbon stock present in each centimeter of soil depth down to a meter. And what hopefully you can see it visually, that the green line is a lot broader on the native grass than the planted pasture. So one of the important lessons we've learned, and some of us had a hunch it was going to be, we were going to come to this sort of realization, is that not all green stuff growing in a pasture performs the same way. That I think we will find, and we will document, we're starting that already, that with native plants, we find rooting depth, microbial biomass, everything is significantly higher at depth, all the way down to a meter or deeper is what we've measured, highly significant differences. So any soil carbon sampling protocol or strategy that only measures 15 centimeters deep is missing the story and absolutely shortchanging the farmer, because the real benefits are happening at depth, not at the soil surface. And unfortunately, most of the quicksilver carbon market plays are modeling based and are 15 to 30 centimeter deep, so they're missing the story. So what does this look like? So this is a fence line right between these 2 photographs. Exact same soil type. 10 years ago, the brother on the right decided to do this adaptive multi-paddock grazing, and you can see hopefully the darkening of the soil. That's organic matter, that's organic carbon, and it's minerally associated organic carbon. On the left, you can see how shallow, and I didn't put a scale on this, but what I wanted to share was the difference in infiltration rates. So on the brother on the left has a 1 or 2 centimeters per hour infiltration rates. The brother on the right in this clay loam soil has 27 centimeters per hour additional infiltration. So not only is the soil carbon important for maintaining the viability of the plant community and helping with climate mitigation and food quality because of the additional nutrients that the organic matter can hold on the right and moisture that it can hold on the right, but there is a significant downstream benefit to flood damage reduction, water quality improvements that we'll take a few minutes to talk about a little later here. So one of the things we did as a group with Shell Oil Company is we said, well, what would the benefits of, under different scenarios, be of converting pasture land to this multi-paddock grazing? And then also we have another project going in parallel with what's called low disturbance cropping, where they're doing 1 pass no-till with tillage equipment, no-tillage equipment that only disturbs 1 to 2% of the soil surface, rather than about 30 to 20 to 40% of the soil surface, which is what's typically disturbed by conventional no-till. So currently, if you look at the emissions of greenhouse gases from farm soil erosion, fertilizer and crop production and livestock production, on the far left side of this graph, if you just did what IPCC suggests, they've suggested wholesale ruminant reductions across the planet. You come to scenario number 2, there's really no significant change in the farm soil erosion, which is the biggest source of greenhouse gases. And the fertilizer and cropping emission reduction doesn't occur. And it's a de minimis reduction in greenhouse gases from reducing ruminants. And then we said, what if we took 25% of the cropland, that 1 billion hectares, if you recall, and 25% of the 3.5 billion hectares of grazing land, and we converted those to amp grazing and load stripped cropping. And there was an immediate, the flip below into the negative zone on this curve shows that, wow, what a big change. And we still have an erosion, farm erosion source and a fertilizer manufacturing and cropping source of emissions, but we've converted potentially all of the ruminant emissions negative. So the potential is, really, to convert it into a positive by converting it into a negative. And 50 and 100% conversion scenarios that we modeled suggested just even off the chart benefits. So this got us all excited about the other possibilities for scaling. And one of the things we looked at, and I want to just go really quickly through this. Nobody has any sense of how long-lived and how durable soil organic carbon is. Everybody thinks trees, store carbon for long periods of time, and they can, but most of the tree carbon is stored for long periods of time when the trees are carbonized by fire and they fall over and become incorporated into the soil system. So trees add value to carbon on the planet, but at this point in time, and in the future, absolutely even at a higher risk, trees are at a very high risk as a carbon stock, as a place where carbon is managed. So here's a sense of how old some of these carbon stocks are in the soil. In Wisconsin, where we measured it, you go down 1/10 of a meter, so 4 inches, whatever it is. The average age of the carbon is about 100 to 200 years of age. You go down 1 to 2 meters, and the average age is 1,500 to 12,000 years of age. You go greater than 2 meters, and it's greater than 12,000 years of age. In some places, 80,000 years, 100,000 years of age. And that's not peat. Peat is a whole nother story. If you go to New Mexico, where we're doing a project, this blew me away. 1/10 of a meter down, 100 to 200 years of age, 2/10 of a meter down, 30,000 years of age, greater than 2/10, 3 to 5 million years of age. Attorneys that write contracts that use the word perpetual have no idea what perpetual means, and nature has a completely different definition of perpetual and permanence. And it just blows me away to think about this durability, and we're focused on trees at the wrong time when we should be focused on soils.
Hey, Steve,
so now I want to just
can I ask you a couple questions before we get away from this? One of the questions that both Ray and Chuck and maybe Carrie at the Natural Lands Institute talk about is what are the reasons? So as Ray says, he studied this at Texas A&M in the early 80s, and it was called high intensity, low duration grazing.
Right.
And then Chuck asked kind of what are the barriers to it? Is the cost of fencing? And so kind of why hasn't it caught on? And then Carrie or somebody at the Natural Land Institute also asks about how to incentivize. So farmers are being paid through carbon markets for cover crops. Is this multi-paddock grazing part of this? And if not, how can we incentivize farmers through the carbon markets for this practice? So maybe a little bit about the push-pull.
So big questions with long answers. Let me refer you, I'll answer some of the questions real quickly.
Yep.
But let me refer you to Vimeo and look at the Soil Carbon Cowboys videos. We've got 10 of them now.
Yeah.
And then look at the Patagonia Provisions Unbroken Ground movie, and you'll see answers to some of these questions. So the first thing is soil carbon has a de minimis value at this time. And the real value is in improving stocking rates. If the cattle drive the economy of the ranch, and if their soils are depleted and the grass is depleted, the grasslands are declining, their ranch is declining. And most ranches are in a tough place. But by adding more cattle, 3 to 5 times the stocking rate, that will drive they don't need other incentives. Helping them with transitional financing to be able to buy the additional livestock is one thing that we're working on, and I won't take time today. The primary thing that's needed is education. And there are barriers that are moving out of the way. Mm-hmm. The growth rate in this adaptive multi-paddock grazing around the country now is between 30 and 40% adoption. So it's off the charts. And it's happening with indifference to Farm Bill and with indifference to the normal rancher farmer incentives. The way it's happening is by we're working with groups that are handholding the ranchers. You know, Gabe Brown, Alan Williams, Understanding Ag, General Mills, you know, McDonald's, Cargill, all sorts of organizations that are concerned about their beef supply chain and the health of grasslands are stepping up, stepping in. You know, Dannon and you know the dairy industry is doing the same to try to figure out how to ensure their supply chains of milk and meat and so forth. So the carbon marketplace has potential, but at the per acre value for many farmers, it's going to be de minimis. It's going to be, you know, partially on the edge of the plate. But the real value proposition is improving the land so that the driver, the meat and the milk and other commodities can be produced at larger scales without disrupting more land, just intensifying the use and using the land in a way that's more productive for the land and better for the land. So water infiltration. So now I'm switching to the southeastern US, the same water infiltration equipment on 5 pairs of ranches, conventional paired with the adaptive multi-paddock ranches. And so pair 1 is in northern Kentucky, there's a Tennessee pair, and Alabama, a couple of Alabama pairs, and a pair right about an hour north of Baton Rouge on the Mississippi side of the state line. And with the exception of pair number 1 in Kentucky, which I'll explain in a minute, all the other ranches in the AMP grazed setting had significantly to very highly significantly improved infiltration rates on AMP rather than the continuous conventional grazed. You know, the difference was, you know, gosh, one to sit nearly 6 inches per hour in the AMP over the rate that was measured in the conventional. That's phenomenal. I mean, an acre inch of water is about 27,000 gallons. If you have an acre foot, which is about 330,000 gallons, and let me stick with an acre inch. If you have an acre inch, you have 27,000 gallons, and you infiltrate that over 1 million acres of land, and instead of run it off into the local stream, it completely changes the in-stream flows, reduces flood flows, you know, reduces the impact to bridges and roads and, you know, safety and so forth. This is really highly economically valuable. So this incentive alone, having more available moisture in their soil for growing the plants, producing the forage that feeds the livestock, that is incentive enough for most ranchers. They don't have to irrigate. They don't worry about droughts. Their ranches are green when there's a drought, and all the other ranches are brown. So that is incentive enough. The ranch in Kentucky, we tapped into a shallow soil over limestone on the continuous grazed, and we could pour, it's karst, it's cave country. We could pour as much water onto that soil. We could bring semi trucks and pour it, and it'll go right into the soil because it's really going into the karstic limestone below. So that's the, in Kentucky, the continuous graze, the CG ranch had the higher infiltration rate because of the connection with the bedrock. So the other really intriguing finding was breeding bird work that we did compared across the paired ranches. And 4 o'clock in the morning, we get up and go out, do the bird work. That's me leaning on a shovel. It was an early morning. And that's Mike McGraw with Res, AES, former AES Res now. What we found just blew us away. We found that rare obligate grassland birds were off the chart using the adaptive multi-paddock grazed paddocks and turning their backside, literally, if there was a fence between the two, they were turning their ass end and pointing their ass end toward the conventional graze. The older male grassland birds were using the fence as a territory divide and literally perching on the fence and paying attention to the amp grazed side of the fence. So when you find in the southeastern US where obligate grassland birds are already rare, when you find disproportionately high numbers, the orange histogram bars are this is the species richness for obligate grassland birds at the top, ecotonal bird species, then forest generalists. We found the adaptive multi-paddock grazed birds in the adaptive multi-paddock grazed ranches, just off the chart more abundant, higher richness, higher diversity, and populations. And this was another discovered lesson, ranch number 2 in Tennessee, that rancher, conventional rancher, because they'd experienced years of drought for the past 8 or 9 years, he's let his grass grow out before putting livestock on it every spring. And then he comes in and harvests hay. So he has winter hay and doesn't have to buy in feed in the winter. And the grassland birds, the rare birds, responded to that grow out, that allowance of, the grass to grow. So he had much higher rare obligate grassland bird use on his farm than the neighboring amp grazer. But during a normal growing season, that guy wouldn't let his grass grow out. And he would not have allowed breeding success of the rare obligate grassland birds. So the abundance, it's just off the charts for these rare obligate grassland birds. So what it told us was that, wow, these are the birds that have declined and are declining at a 70 to 90% rate per year since the 70s. Many of these grassland birds have declined by at least 90%. And it looks like amp grazing may be part of the conservation solution for these birds. We're testing this now in Canada across 3 provinces, and we'll be moving our research to the northern US Great Plains next year and testing this again. So what an amazing conservation story. I never thought grazing would be part of, livestock grazing would be part of managing rare birds, at least at the scale at which it seems possible here. So the other thing we looked at was vegetation composition, diversity, biomass, forage quality. And with regard to forage quality and quantity of forage, what we found was the amp grazed pastures had significantly higher biomass, significantly higher crude protein, and many other plant nutrients that are necessary for not only the grazing livestock, but wildlife, were significantly higher in the AMP grazed as opposed to the exact same forage plants, the exact same species we chose right across the fence in the conventional grazed. So what the farmers, the ranchers were realizing was significantly higher cattle weight gains and much improved health, much lower veterinary bills for their cattle. In fact, no veterinary bills in some cases. We also found higher plant and biomass overall, and fine litter, less erosion that was measured, less bare ground, significantly higher soil carbon accruals, and we'll be reporting on 2 years of flux tower greenhouse gases sometime in the next few months. But it looks like significantly lower outgassing of greenhouse gases from the AMP grazed. And then we did some pretty cool things with hyperspectral and multispectral imaging. Fugui Wang at AES, now RES, actually mapped down to the species, invasive plants over the landscapes and native plants, and mapped standing crop biomass very precisely. And we found that there's some suggestions that are needed. Most of these ranchers, if it's green and the cattle eat it, they're very pleased. But the real solution to climate and improved water and biodiversity is not to just default to non-native plants and invasive plants, or even planted, cultivated agronomic plants in their pastures, but really figure out how to incentivize them to restore native plant communities. That the pastures that were the most lively. We also have entomologists and all sorts of other researchers on this team, and the butterflies and the pollinator bees and pollinator beetles, the life that was associated with the paddocks that had native plant species dominance was off the charts compared to those dominated by cultivated agronomic species. And I think with that, the team is a wonderful team of a lot of researchers, including some Michiganders there, Lisa, from MSU, Jason Roundtree, and a number of other folks from MSU, Swanson, the animal welfare person group from MSU. So just a wonderful team of people, and we're now moving it to the Northern Great Plains on the US side, and then we'll have the data sets that we need to really begin modeling how improved grazing can be useful for addressing climate, water, food quality, food security, animal well-being, rancher well-being. So the socioeconomists are working with us, ecologists. It's really a fantastic process. So I think that is it. I've got this one other slide that we've prepared that really has, we generated this for the country, and it really shows the highest probability areas for actually, that are in need of soil carbon improvement, and where the soil carbon improvements can be of different magnitudes. So I think that there's questions, Lisa, maybe now would be a good time to.
That sounds great. Yeah, let's jump into a couple of them. A question from kind of Woody and Steve. The question about, so Woody's question is about, can you comment on grazing with different animals, goats and sheep?
Yeah. What we're finding is that grazing that emulates mixed herd, mixed cohort, age classes, mommy and daddy and baby and little baby and teenage, rather than dividing the herds up, when you bring it all together, including additional species, that the benefits actually seem to be better. And yeah, there's a lot of synchronicity. One animal, one age class will eat some sort of plant, and then the other will come in and follow-up feed. And when you have multiple species, the follow-up feeding is a real advantage. So I think what I've learned is that the real goal of grazing is to beat the shit out of the land, excuse my French. It looks terrible right after the grazing is done. Everything is, 50% is eaten off and the rest is defecated on and urinated on and trampled. And that is what invigorates the whole system. And you immediately move the animals off. And I was kind of confused by that. We've done a lot of travel in the high Arctic, and we've watched 50,000, 30,000 caribou cross a 500,000 acre area between a mountain pass and a lake, and it looks like the most trodden pastures in a Wisconsin dairy farm. And you come back 1 year later, although the caribou might come back 5 years later, they might not come back every year, and it is stunning. Just stunning how lush and diverse and the life and it. So that's the bullseye here. And if we had native plant communities that were grazing and grazing very quickly like this with long recoveries, so far we're not measuring declines in native plant diversity. We've got a very detailed paper coming out on that, and not measuring declines in insect diversity, I believe, will be reported by Jonathan Lundgren. So really intriguing.
Yeah, great. Okay, well, thanks. Let's get to another couple others. So Steve asked, so this is large scale. So what kind of, for those of us doing smaller grassland conversion, what can we take from this?
Well, I think the primary takeaway for me at all scale is the foundational principles on what the relationships were historically that we could really learn from and emulate. And that can be done at any scale, whether you're grazing hamsters in your lawn, chinchillas, whatever it is, or one or two goats, at your farm. It doesn't seem to matter. The principles have universal, practical, universal application at any scale. Is the sense I get.
Right, and I think isn't the subtitle of the Unbroken Ground movie something like a new old way to grow food?
Right.
Like that's what we need to emulate. Okay, so Emily asks a question about balance of nutrients. And so I think it's related to the kind of idea in the beginning where you were having the theoretical, if we added 1% more, and then in some places you were finding 2 and 3% more. So I think her question is about, does that upset the balance of nutrients? Is there anything in that?
Actually, the balance is so terribly upset already. What we have measured, so one thing I didn't point out, and I should have, we have elevated the value of reference natural areas in every one of these studies.
Yeah.
So wherever we can, not only do we find an AMP and a CG pair across the fence, but we look for the most local reference natural areas, native grasslands. And what we found in every circumstance, and we do the same measurements on the reference natural areas where there's no livestock grazing usually. What we found is that the soil carbon levels are 500 to 700 tons per hectare, 900 tons per hectare, as opposed to 100 tons per hectare in the depleted landscapes. So by adding back soil organic carbon, we increase the water holding capacity. Every 1% organic carbon, depending upon the soil texture, adds a water holding capacity of about 12,000 to 60,000 gallons of water per acre. We also add soil colloids, which are binding sites that hold nutrients, hold organic matter, provide niches for fungi and bacteria. So we are in a massive rebuilding need right now. The soils on the planet, if you think the vegetation and natural areas are depleted, the soils on the planet have suffered a far worse trajectory. So it's all about rebuilding.
Right. Well, Steve, we have come to the end of another hour. There are more questions. And so because this is just such a fascinating topic and it's such a time for it to be adopted, as Ray said, he's studying it in the 80s. And I think, wasn't Carter promoting solar and wind in the 70s? And so sometimes it's just these things take their
Yep.
time, and now is the time, and it's all hands on deck, right? So Steve,
Exactly.
I want to thank you. As I said, it's been too long since we've had a chance to catch up, so we'll do that a little bit more. I want to thank you all online for joining us. Great to spend another hour with you.